So hi, I'm Louis Pilfold. I started writing Elixir and Erlang a couple of years ago, and through various pet projects, I went from knowing nothing about compilers to somehow having a little language on the beam. So I learned about tokenization, parsing, abstract syntax trees, and code generation, and what this can look like in the context of Erlang and Elixir. So I'd like to share this journey with you, and also share some of the things I've learned along the way. So when I discovered Elixir, I was professionally writing Ruby. Back in the Ruby world, I developed a soft spot for static analysis programs, one of which was a style linter called Rubicop, which is a program that inspects your code, finds stylistic errors and common mistakes, and alerts you to them. So I find they're handy for keeping a code base nice and consistent, and also avoiding arguments about indentation. So being a young language, Elixir didn't have an equivalent tool, so I thought I'd have a stab at making one myself. So lintas are effectively functions that take some source code and then return a number of errors to the user. So I didn't know exactly how they worked, so I looked at the source for Rubicop and another JavaScript linter called JSCS, and I discovered that when you look a little closer, they look something like this. They take some source code, they convert them to one or more different data structures, and then analyze those forms in order to find any errors. So these errors would show up as patterns in the data that we can match against. So the first data structure that we can create from source code is a list of tokens. Tokens being the smallest elemental parts of the source code we type. Oh wow, you can still hear me. That's great. The smallest elemental parts of the source code we type, the basic building blocks of code. So for example, if we took the English sentence, hello world, and tokenize it, we might end up with something like this. We have 5 tokens. The first one is a word with a value of hello. The second one is a comma. The third is a space. The fourth is a word with the value of world. And lastly, we have an exclamation mark. So we can do the same for Elixir code. So here's a snippet in which I pipe the number 1 into a function called add. And the function also takes an additional argument of 2. Except that's a syntax error. Never mind. When tokenizing, it becomes a list of 4 tokens. The number token with the value of 1, an arrow up token, which is the pipe operator, an identifier token with the value of add, and the number 2. So in Elixir terms, this data would look like this. Each token is a tuple, where the first element is the name of the token type as an atom, and the last element is the value of the token. And in the middle, there is some metadata, which I've omitted. So in the Ruby and JavaScript linters that I looked at, the tokenization process was quite large and complicated, as they had to implement a tokenizer from scratch. Luckily, this isn't the case in Elixir. The Elixir compiler is written in Erlang, and thus we can call it from Elixir. And the modules are available in the standard library. So Elixir tokenization are as simple as calling the tokenize function from the Elixir tokenizer module. So getting the tokens is easy. How might we use them in a linter? So one simple thing a linter for Elixir might want to do is forbid the use of semicolons to separate expressions. Each expression should instead be separated by a new line, which is much more common and idiomatic. So to make the linter detect violations of this rule, I first define a function called semicolons that returns true if passed a semicolon token and returns false if passed anything else. And it detects the semicolon token by pattern matching on the first element of the token tuple, which in this case is the semicolon character as an atom. So now with this function, I can use enum any to iterate over the list of given tokens and return an error if any semicolon tokens are found. So tokens are simple and easy, but quite limited. In order to do more meaningful analysis, you need another form to represent the source code. This form is an abstract syntax tree. So while tokens were the linear sequence of the elemental components of source code, an abstract syntax tree is the representation of the syntactic structure of source code. So here's an example. On the first line is some code in which the function add is called with the arguments 1 and 2. And below this is the tree this expression would form. So the root node is a call to the function add. The call has 2 leaf node children. The first is the number 1, and the second is the number 2. And here's a slightly more complex example. At the root of the tree, there's a call to the send function, which has 2 arguments and thus 2 children. The first is a call to the zero-arity function self, and the second is a tuple. So the tuple has 3 elements, and thus the node has 3 children. They are the atom compare, a function call, and the number 1. And the function call is to the plus operator, and it has 2 children, each of them the number 2. So normally one would get the tree by first tokenizing the code and then passing the tokens in order to construct the tree. But in Elixir, there's an easy method thanks to the macro system. So when the quote special form is called and an expression, it returns the Elixir abstract syntax tree for you to inspect or manipulate. So Elixir's EST is quite concise and simple. Everything that's not a literal in the EST is a 3-item tuple, where the first element is the name of the function or the constructor, and the second item is some metadata, and the third is the children in a list. So here we have the add function again, only this time the quote special form is being used to get the tree. At the root is a function call, so it's a 3-item tuple. The first element is the atom add, as that's the name of the function. And the third element is the node's children, which are the numbers 1 or 2 in a list. So now I've learned a little about an AST and how to obtain it. I can use it in the linter. So say I want to forbid the use of the unless macro with an else clause, as I think it would be better written as an if in order to prevent the double negative. So with an AST, I can enforce this by walking across the tree until I come to the offending pattern. And the offending pattern in this case is a node with the atom unless in the first position, making it a call to the unless macro, and then an else block in the second child of that node. So traversing the tree is actually quite easy, thanks to the macro pre-walk function provided to us, which takes an AST, an accumulator, and a callback that will receive each node in turn. So I have this check unless callback with 2 clauses. The first one pattern matches against the offending nodes and returns the atom error in place of the accumulator. And the other is just a catch-all for all other nodes. All other patterns, except for the offending one, are valid, so we just return the accumulator. And so with that, I have the beginnings of a working linter. And I've also learned about tokenization and abstract syntax trees, and a little about parsing in general. So through the macro system and associated helper functions, Elixir has made this task much easier than maybe it would have been if I tried it in JavaScript or Ruby or elsewhere. All that was left is to do some plumbing to present the errors to the user, and then maybe write a few more rules. And after writing a few more rules and then experimenting with macros myself, I started to feel pretty comfortable working with syntax trees, giving me the first part of that compiler puzzle. So sometime later, I found myself writing a simple web app in Elixir. Nothing exciting, it just rendered some HTML pages to the user, and they gave them some forms which they can use to record data into a database. So while I was writing the HTML views, I found myself getting a little fed up of the default templating language, EAX. It's fast and easy to use, but I still have to write HTML, which I don't think is the most fun thing to do. So it has lots of superfluous angle brackets and a rather verbose syntax for closing tags, and I have to manually escape certain characters, and I'd just much rather not do this. I want to type something much more concise. And when working with Ruby or JavaScript or Haskell, I can do this. So there's a templating system for Ruby called Slim, and another for JavaScript called Pug, which allow me to write HTML like this. All the superfluous syntax is gone, and the delimiters have been replaced with indentation. Granted, it's not everyone's cup of tea, but I've become rather used to it, and as a result, I found myself wanting something similar in Elixir. Armed with my newfound knowledge of tokenization and parsing, I decided to have a go at trying to make the same thing for Elixir. So the templating library is effectively a function that takes a template of alternative HTML syntax and returns a function that, given data, produces a string of HTML. In order to know what HTML to generate, I need to, yet again, do some analysis on some source code. So, like with the linter, I need to generate an abstract syntax tree, which I can then expect and do things with. So unlike the linter, I don't have a pre-built function for getting tokens from my HTML templates, so I have to build my own tokenizer. After a little digging, I discovered that the Erlang standard library contains a module called Lex, which offers a DSL for creating tokenizers. This is also the same module that the LFE language uses for tokenization, which is a pretty good endorsement in my books. I should also say It's probably a little over the top to do this here, as I could probably easily parse a string using pattern matching, but this seemed like a good excuse to learn something new and fun and potentially useful. So one line is one element in my syntax, so I'm just going to split on new lines and trim the indentation, leaving me with just the element that I'm interested in parsing. So looking at these elements, I can see a few token types. There is one for names, which are element names, class names, ID names, and so on. There are ones for dots and hashes, which I use to denote classes and IDs respectively. The syntax for attributes includes open parens, close parens, and then a little equal sign to go between the attribute name and the value. And there are strings, which are a series of characters surrounded by double quotes. So lastly, there's Whitespace tokens and word tokens. And word tokens are any non-Whitespace character that any of the others don't match. So now I can teach Lex what my tokens are and start building the tokenizer. So a Lex module is a file that contains some Erlang-like code and has the file extension XRL. Within it has three sections. Definitions, in which the author uses regular expressions to define a pattern for each type of token. And the rules section, in which the author declares a data structure that is to be formed for each token. And then lastly, the Erlang code section, which contains helper functions which you might use in the other two sections. So here's my Lex definition section containing all of my various token patterns. Names are capitalized and go on the left-hand side of the match operator, and patterns go on the right. So it has simple literal patterns for dot, hash, EQ, open P, and close P. And after that, we have more complex patterns, such as string, name, whitespace, and word. So regular expressions can be a little hard to read, so I'm just going to quickly go over them here. So the string pattern is a pair of double quotes with 0 or more characters between them, where the characters are any non-double quote character or any character preceded by an escaping slash. So this is how, with regexes, we can get support for escaped quotes inside string bodies. A name is any letter followed by any mix of letters, numbers, underscores, or dashes. Whitespace is just spaces or tabs. And then a word is anything else. So after the definition section comes the rules section, which is a mapping between patterns and a token data structure. So the syntax for a rule is the name of the definition in curly braces on the left, and then an instruction tuple on the right, and a colon in the middle. And because this is Erlang, everything ends with a full stop. So the first element in the tuple is the atom token, which is an instruction to output a token for when this pattern matches. The second item is a data structure that we want to form. Here I'm always forming two item tuples with a token name as an atom in the first position, and then the match characters in the second position, which I access through the magic variable token chars. And so some of these definitions overlap and will match the same text. For example, name and word. So in order for the tokenizer to always produce the same results, the order in which the patterns are used to test matters. So with leaks, rules are tested from top to bottom, and the first one that matches is used, much like a case expression. So if I place this file in the source directory of an Elixir project, Mix will compile this into an Erlang module for us, which exposes a string function. This function takes a char list of code and returns a list of tokens. And because I used two item tuples with an atom as the first element, I get back an Elixir keyword list. So here I'm tokenizing a line of code, and I get back a name token with a value of div, a whitespace token, a name token with the value of hello, another whitespace token, and a name token with a value of world. Cool, so at first this seemed like enough, but when tokenizing another line, I discovered a problem. So when I receive a string token, the value of the string is as written in the source code, when I actually want the value of the string. See, it has the quotes around it. So to resolve this, I can make use of the final section of the leaks module. So here I've updated the token tuple for the string to call a function called string on the token chars before inserting it into the tuple. So the definition of this helper function goes in the Erlang code section, and it simply gets rid of the quotes by dropping the first and last characters using the drop last and tail functions. So now I get the value I want for string tokens, and later I may also want to add additional helper functions for passing numbers, handling escaped characters, and so on. And with the tokenizer done, I can move on to building an AST from the tokens. And in the same way that Erlang supplies a tool for tokenization, it also supplies a tool for parsing, which is the YEK module. So like Lex, it's used by writing a module with a specific syntax and file extension, which is then compiled into an Erlang module. And this module contains a grammar, which is a set of rules that describe the syntax of a language. So the file consists of 5 main sections, which are non-terminals, terminals, the root symbol, a set of grammar rules, and another Erlang code section, which is used for helper functions. So terminals are the most basic symbols that are recognized by the grammar. They cannot be broken down into smaller parts. In this case, they are the token types, which my tokenizer can create. So non-terminals are higher level symbols, which are formed by composing together terminals, other non-terminals, or a mix of both. And the root symbol is the highest level non-terminal in the tree that composes all the other ones. And lastly, grammar rules are definitions about what symbols compose other symbols and in what context they do this. So let's look at some of my non-terminals. An example non-terminal in my grammar would be a class literal. So in the first line, the first code example, there is a h1 element with the class of Jumbo. It tokenizes into 3 terminals, which are the name h1, a dot, and the name Jumbo. So in this context, the dot terminal followed by the name terminal can be composed together to form a class non-terminal. So a class is a dot and then a name. And likewise, an ID is a hash and then a name. So elements can have many class literals on them. So we need a classes non-terminal. And classes are either a single class or many classes. And a repeating symbol like this is defined recursively. So here, classes can be a class, or alternatively, they can be a class followed by classes. So names is the head of an element in my shorthand syntax. So it can be a name, or a name then ID, and then a name then classes, or a name then ID then classes, or just an ID, or an ID then classes. And these declarative rules continue. I've got to define a rule for attributes, many attributes, pieces of text, content, which is formed from composing many pieces of text in Whitespace together, and so on until I've covered every symbol all the way up to the root symbol. And here my root symbol is an element. So an element is either just a set of names, or it's names followed by attributes, or names, attributes, and then content, or just names and then content. And so now that I have definitions for all the different symbols, from the lowest terminals to the root symbol, non-terminal, and YEK has enough information to be able to parse a single element from a list of tokens. The only thing that's left to do for it to be able to actually build a tree that we can use is to instruct it how to build a data structure for each node, for each non-terminal. So in the mini AST, I want the class token to be represented by a string with the same value as the token. So to achieve this, I need to be able to refer to the tuple which makes up the name token, so that I can extract the string value from it. So helpfully, YEK assigns pseudo-variables in the form of atoms for each symbol used in a non-terminal definition. So if a class is a dot then a name, atom $1 refers to the dot token, and atom $2 refers to the name token. The string I want is the second element in the tuple, so I call the element function on $2 in order to get it, and the code is placed after a colon, after the rule, but before a full stop for each definition. So now that I've defined a data structure for class, I can do the same thing for ID. And it also just pulls the string out of the name token. Some of the nodes in my ASC will be represented with a list. So one such example is the classes symbol, which is one or more class symbol. So for the base case of just one class, I can just wrap it in a list. And for the case of a class followed by classes, I can just prepend the class to the value of classes. And this will unfold recursively until we have just one class, which is the base case at the top. So other symbols are more complex than just a simple value or a list. The name symbol consists of a combination of an element type, such as a div or body, an ID, and then one or more classes. So we could represent this with a 3-item tuple, but then it's really hard to remember which field is which with tuples. So instead, I've opted to use an Erlang record. Like Elixir structs, each field in a record definition gets a name and a default value. And here I have the names record, and it has a default value for the type field, which is div. The default value for the ID field is the atom nil, and then the default value for the classes field is an empty list. So with this record, I can use a nice syntax for setting and getting named values on a complex node. So now that I can build simple values, more complex values, and collections of values, I can work my way all the way up to the root symbol, which is the element. So an element here is a record with a type, an ID, some classes, attributes, and lastly, content. So for each definition, I can use the dollar variables to set the various fields from the child nodes, and then with that, all the definitions are in place. I can place this file in the source directory of an Elixir project, and then Mix will compile it to an Erlang module for me. So I can now turn source code into tokens, and tokens into an AST. The next step is turning an AST into a function which produces HTML. So I wasn't entirely sure how to do this. So I had a look at the source code for EAX on GitHub, and I discovered that the code leverages some of Elixir's metaprogramming features in a way which seemed pretty clever, but also quite easy to imitate. So yet again, like with tokenization, Elixir's done some of the work for me. So here's an EAX template, and the function that the EAX compiler would construct from that template. The function simply concatenates each part of the template together. So let's look at how this is done. So the EAX's parser splits the template into text and paragraphs. The template in the first code snippet would be split into the text hello, and then an expression consisting of the variable name. So this list is then turned into an expression, which can be used as the body of a function. So here's a compile function which constructs some expressions. It first reduces over that list with the cogen function and uses an empty string as the starting value. And the cogen function has two clauses. The first one is for text elements, which it concatenates onto the buffer, and doing so inside a quote block like this results in the tree being returned rather than the expression being evaluated. So the other clause is for expressions, and it works exactly the same way as the previous clause, except it calls code string to quoted on the value in order to turn it from a string of Elixir code into an expression which is part of the AST. So here the compile function is called on the list from before. It's a little hard to read these expressions. So at the bottom, I'm converting it back into a string with the macro to string function. And then on top, there's the function from before. And on the bottom is the string that was just returned. And they're pretty much identical. So how would this work for the HTML templating library? So the parser is used to generate an Elixir data structure with all the required information for the templates. And from that data structure, a list of fragments of HTML and text and expressions are formed. This list is put through the same compile function, which results in an Elixir AST being built with the string values injected into it. And then all that's left is to turn it into a function. So if I want the AST I've generated to be the body of a function, how do I do that? Well, it turns out that def, as seen before, was not a keyword, but instead a macro. And as a macro, I can use the unquote special form to inject an AST back into the code as an expression at compile time. So to build the function, a template is tokenized, parsed, compiled, and then unquoted into the block of a function. So now I have the beginnings of a HTML templating library that I can use in a real app. Except it's still missing a few things. I probably want to add a looping construct so I can iterate over collections, and I probably want conditional expressions so I can have more dynamic templates. And I would add these by adapting my tokenizer and parser to output a new type of node for each construct. And then in the cogen function, I can define a new clause which constructs a new AST that gives the behavior that I desire. So it's about this point I sort of realized that with relatively little effort, I had created a program that takes some source code, parses it, and then generates some code which is executed by the virtual machine. The output of my program is a set of functions. Without really knowing anything about compilers, I've sort of, if you squint, written a micro language for the Beam. And getting this file was easy thanks to the excellent tools that were supplied by the Erlang ecosystem. So I thought presumably it wouldn't be that much harder to create an entirely new language using the same tools. And as a language nerd, this really excited me, so I jumped right in and abandoned the other project. I will finish it. So here's the language. It's called Gleam. I believe that in order for a language to be worthwhile, it needs to have a really clear idea of the problem that it's trying to solve. And the problem that Gleam is trying to solve is that there's just not enough curly braces on the beam. After all, how are we going to convince the JavaScript community to join us? So the first step in solving this problem is to make a tokenizer. So I've got only a few definitions. I've got a float and an int for numbers. I've got a string, an identifier, an atom with quotes, and lastly, whitespace. The first Parser rules are the keywords, delimiters, punctuations, and tokens, which are all very straightforward. So after that comes the more complex tokens that use patterns from the definitions section. So the value of each of these tokens comes from calling a helper function on matched characters. So the int function converts the value to an integer, the float function converts to a float, for an identifier and an atom, I convert to an atom. And for strings, I get the contents by dropping the quotes as before. So these functions are all defined in the Erlang code section. Also note how the int pattern and the float pattern are both being used to construct the same token. So Lex allows multiple rules to construct the same token, so we can have some variations in syntax like this. So lastly, there's the rule for whitespace. Instead of constructing a token, I use the skip token atom in order to signify that text matching this pattern is to be discarded. Whitespace has no meaning in Gleam, so it can be safely ignored. And that's the basic tokenizer done. Later, I'll probably want to extend it with mathematical operators and the pipe operator and maybe some syntax for maps. But for now, I can just move on to the Yek parser. So here is a Gleam module called stack. It's made up of multiple statements, the module declaration at the top, and each of the function definitions are module statements. So the root symbol of the grammar is a single module, and a module is defined as a series of statements, and statements are defined as one or more statement. And a statement is either a module declaration or a function. So module declarations are simple. They always have the module keyword followed by an identifier. And both of these are tokens, making them terminal symbols and leaf nodes in the AST. So to make working with nodes a little easier, I've used Erlang records for each one. The module declaration has a name field in which I place the value of the identifier. Moving on to the other type of statement, a function is either the public or private keyword, followed by an identifier and then a function block. And the resulting function record contains the function publicity, the name, and the clauses, which are taken from the function block. And a function block is a pair of curly braces around one or more function clauses. Later, I would imagine there'll be other function block contents, for example, doc strings or maybe unit tests, which is why I've used a record for this block, as using a record makes things very easy to extend, as I can just add another field. Next, a function clause. It's the def keyword followed by an arguments tuple and a clause block. And again, I'm constructing a record. This one has fields for arity, arguments, and the body. And this continues for every parser symbol until I've defined a rule for every node in the syntax tree. So there's all the nodes that currently make up the Gleam AST. Each one is a record. This makes it easy to extract the values from them. But in addition to that, it also provides a handy method for pattern matching on each node, which will be quite useful later. So the next part of the simple compiler is to convert the Gleam abstract syntax tree into a format that can be fed into the virtual machine. So with the templating language, this format was Elixir AST, which again would work here. However, there are also other options. Since we've come all this way just using the OTP standard library, let's explore one of the alternatives, which is core Erlang. So core Erlang is an intermediary language used by the Erlang compiler. So when regular Erlang code is compiled, it is converted into core Erlang code before being optimized and converted into the bytecode that the virtual machine actually runs. So if I target core Erlang rather than trying to generate bytecode myself, Gleam will hopefully benefit from all the same compiler optimizations as Erlang and hopefully be as fast. So core Erlang has a textual representation, which is quite pretty, which you can see here. These code snippets are equivalent. The first one is Erlang, and the second one is core Erlang, which, as you can see, is much more verbose and explicit. So you have to write guards, and function application requires an apply keyword, and so on. But in addition to the textual form, it also has an abstract syntax tree consisting of regular Erlang data structures, primarily records, which is great, because if it's just regular Erlang data, I can just construct it manually. Well, not quite, because the official documentation states that core Erlang AST is subject to change at any time without notice. It may be that when the next OTP arrives, the core Erlang tree looks completely different, and I have to rewrite this section of the compiler from scratch. So if the AST format is not formally specified, how can it be generated? So the answer is to use the CL module, which exposes functions for the composing and decomposing of this AST. So the decomposition functions could possibly be useful for reflection in a similar fashion to how the Elixir linter worked. But for the job at hand, I'm interested in the functions used for composing the tree. So here we see the catom constructor being used. It's a function which takes an atom and returns the core Erlang node that represents an atom. What exactly this looks like doesn't matter. It may change in a later version of OTP. The only thing that matters is that we trust that this function will always return the correct node data structure, whatever that may be. So there are similar functions for all the other possible types of nodes. With these, I can convert a Gleam AST into core Erlang AST by traversing the tree and calling the appropriate constructor for that node. This is where the Gleam parser's use of records comes in handy. If I can define a function which takes a Gleam node and then returns a core Erlang node by defining a function clause for each record, I'll be able to cover my entire tree. So for example, here's the clause for the string record, and thus the string node. It just calls the C string constructor on the value from the string record. Next, we've got clauses for numbers. So the Gleam AST doesn't match up perfectly with the core Erlang one, so I have to use a guard to differentiate between ints and floats. And after that, it's just a matter of calling the correct constructor for each type. So all the nodes we've seen so far have been leaf nodes. They've been very simple to convert to core Erlang, while branch nodes are a little more complex. So branch nodes are the nodes that have children. They consist of multiple nodes joined into one. So for example, a list or a tuple will have elements, and a function will have a name and also function clauses. And converting these nodes is more complex, as not only do they themselves need to be converted, but also their children need to be converted as well. So here's a tuple node. Its children are the elements of the tuple. This one contains the atom OK and the string hello. So the children would be the atom node and the string node. In the Gleam tree, this tuple is a record with an elements property, which is a list containing the atom and the string. And the clause that handles converting tuples first has to map the cogen function over all of the children in order to convert them into core Erlang. And then once they're converted, the C tuple function is called on the new elements in order to create a core Erlang tuple. So have I gone back? Here the children live. Yes. So here the children were leaf nodes. They were a string and an atom. But what if the children were also branch nodes? What if one of the children was a tuple, and that tuple contained a list, and so on? So each clause that handles a branch node has to call the cogen function and each of its children. And because of this, the cogen function, when called on the root node of the tree, that node's children will be transformed, and that node's children will be transformed recursively until all the node's children and their children, so on, and the entire tree is converted into core Erlang. So jumping from the bottom of the tree to the top, here is the record module. It is considerably more complex than the previous nodes. The CL constructor takes 3 arguments: the module name, a list of functions to export, and a list of module functions themselves. So And of course, each one of these needs to be given in the core Erlang form. So the name is easy, it's just an atom, so we call the C-atom constructor on the name. For forming the list of exports, I've created a genExports function, which filters the list for functions that are public, and then constructs a core Erlang export for each one. And lastly, functions are transformed into core Erlang by mapping the cogen function over them, which in turn recursively transforms them and their children, and the rest of the tree. So I found that with more complex nodes, it's not immediately obvious how to use the constructor function. If you're going to play with CL, I really recommend downloading a copy of the OTP source code and reading the documentation inside the module itself, and also paying close attention to the type specifications, which can be very informative. When I still had problems, I found a good trick was to turn to the source code of another language that uses this module and see how they use it. Good examples of languages that use it would be LFE, MLFE, and Jockster, which were quite good to study. So right, with a cogen function clause defined for each node in the AST, I have all the basic parts of a Beam language compiler. The only thing that's left is to stick them all together. So here I have a Gleam compiler module, which defines a load file function. The function takes a path to a piece of Gleam source code, reads the file, and then converts into an Erlang string. The string is then fed into the tokenizer, which breaks the source code down into a list of its atomic parts, such as strings, numbers, and punctuation. And the tokens are then fed into a parser, which constructs an abstract syntax tree. And this tree contains all the syntactic information about the code. So lists contain elements, functions have clauses, and so on. The tree is then fed into a cogen function, which converts it into a format which can be loaded by the Beam. Here, that format is core Erlang, which is the intermediary language which the Erlang can pass to. And then the core Erlang is compiled into Beam bytecode using Erlang's compile forms function, and they're loaded into the virtual machine using the code load binary function. So here's a Gleam module. If I call the load file function on it, the file will be read, tokenized, parsed, transformed into core Erlang, and then loaded onto the Beam. And then the Gleam function can be called just like any other function. And with that, there's a 15th language running on the Beam. So I was ecstatic when I first compiled my first module. It just said hello world. It was such a small thing, but it was such a fun journey and an unexpectedly easy and smooth one too. So with Erlang and Elixir, we are supplied with a large range of excellent tools that can be used individually or all together. So Lex and Yek give us an easy out-of-the-box way to do tokenization and parsing of code. And with Elixir macros and core Erlang, we have a friendly way to generate code that can be loaded into the virtual machine. Coupled with Elixir and Erlang's excellent pattern matching and data handling, these tasks become quite straightforward. So I think it would be really exciting to see more projects that make use of what the ecosystem gives us here. I'd love to see more static analysis tools. I'd like to see a code formatter in the style of Go format or Elm format. I think it would also be really interesting to see a language with a powerful ML-style type system on the Beam. Some work has been done here with the MLFE project, and it'd be really great to see that mature and develop into something interesting. I've really enjoyed working in this space, and if you think you could also find it fun, I encourage you to try and build your own Elixir. There's plenty of space for more exciting projects on the Beam. Thank you.
Hello.
Yeah, I just want to make a comment. Yes, implementing languages is fun, right? It's definitely. And it can be very useful. Just that.
I agree, yes.
Stick your hand up if you want to ask a question. Come in.
Excellent talk, super dense, thanks, that's very cool. Did you test drive that while you were building the language? 'Cause that's one of the things I find that's really neat about Elixir is that you can look at the test driving of the language development.
As in, did I do TDD when I was building the language?
Right on, yes.
Yeah, for every single bit of it. I just find it's much faster to test drive anything, because if I have a piece of code that checks if my code works, then I don't have to do it myself. And I'm like ecstatically lazy. So yeah, do it. I've also written a tool called Mix Test Watch, which will automatically rerun your XUnit tests anytime you save a file, so that helps a lot as well, I find.
Any other questions? Has anyone else written their own language? Other than Robert, you can't answer that. You have? Do you have a little insight to it?
So I have a small attribution in getting Louis to build his own language, because I beat him to it.
Thanks, John.
But I didn't use the beam. I wussed out and tried to use, I can't even remember the name of it now. It's what they use for C. Yeah, it's a tremendous amount of fun. It's actually a lot harder than Louis makes out. A lot of it is trying to come up with a grammar for your language that is nice to play with and accurate, something a computer can actually parse correctly. So a lot goes into the language design, which is why copying other languages is the easier way of doing it.
Yeah. That's why I sort of implied my language is completely useless, and I focused only on the compiler, because that was relatively straightforward. I found that Erlang and Elixir gave us so much there. The real hard bit is designing a language which is anyway useful or interesting, which I've got huge amounts of respect for everyone who's worked on like Erlang and LFE and Elixir, because they're all such rich languages.
Yeah, I'm just curious, how long did it take to you to go through this like journey, this process of like researching and getting something done?
So I started writing the linter almost immediately when I started learning Elixir, and it was awful to start with. And I just found that through various little projects, I just accidentally picked up little bits of knowledge about compilers. So there was never a point when I went, I'm going to write a language now, and I got there. It was, as I said, like I got the HTML templating library to work, and I went, oh wait, I've just generated a function. That's really strange. Maybe I could like do that little bit of extra and generate modules and functions, then I have a language. But then once I started looking at core Erlang and stuff, maybe it was, I don't know, maybe a month of evenings. Mostly because I didn't really know where I was supposed to look to find the information about how this stuff works. So hopefully with this talk and maybe some other resources, we can make it a bit easier to get into making languages, because it's really fun.
Thanks.
So I've written a few languages, but I mainly get involved in writing DSLs. Do you actually have seen many people writing domain-specific languages? Because obviously you don't have to write a very rich language. You can write something that's quite very simple. My idea with DSLs is the fact I want to just write the simplest way I want to express what I want to express. Then I just write a DSL for it. So then I've got a language then that does that thing. So I just wondered if you come across many other people that have done DSLs.
So DSLs are very, very popular in the Ruby world.
Yep.
They use all their like just completely insane runtime metaprogramming in order to like build quite powerful DSLs. And I think because of some of the Ruby influence and the fact we've got this really powerful macro system, there definitely is a bunch of DSLs used in Elixir, which are cool and fun. But I think often you can represent this stuff in data quite well, yep. I find. Times in which I think a DSL might be really useful. So I'm really interested in like the use of code for performance. I really want to see people trying to like make musical performances and art with code. And I recently saw a chap write a parser for like a very succinct music notation using Elm. So he could like type his cool little DSL when he'd make a song live. I thought that was a really exciting use of it. But in sort of more big production-y things, I want to ask myself, can I just write some data? Could I get away with just using data here?
Yeah. So the DSL represents data often. But yeah. So the second question I had was, some of the parsers I write are parsing gigabyte files. So did you come across anything for doing like stream-based parsing? So basically, you don't have to necessarily get everything into memory and then go from memory to memory.
I don't know if there are any tools for that that exist already in the Erlang world. Everything that I've parsed has been things I've written myself, and I'm very lazy, so they've always been like 5 lines tops.
Right. Yeah, I don't write the stuff, it just comes to me.
Cool. Thanks very much.